Hello, this is Mrs. Pullen for AP Statistics, and in this video I'm going to provide solutions to worksheet number 2 in the Name That Test packet. So for example 1, we have data from 5 weather stations from Rocky Mountain National Park, and they provide the peak wind gusts in January and April. So the variable of interest is the peak wind gusts. So let me just get a pen out here. The peak wind gusts, which is a quantifiable measure. Even though it looks like we have 2 samples, there are only 5 stations, and they're linking them together, January versus April. So that therefore we would use a match pair T. And it's a test since we're looking to see which one's higher. So we would do a match pair T test. And we would calculate the difference, and I'm going to do January minus April. So I have 35, 9, 26, negative 24, and 17. So with the match pair T test, you're finding the mean of the difference. So we calculated the difference, and that's our goal. And our null is we assume that there's no difference between the results in January versus April. And based on the problem, we want to see if the wind gusts are higher in January. And since I had January minus April, I would expect a positive value, and I'm going to define my alpha as 0.05. So the first thing I'm going to do is go into my graphing calculator, and it's a good idea to start a new document. And I'm going to add a list and spreadsheet because I have actual data. And I'm going to enter those differences. So 35, 9, 26, negative 24, and 17. And then I'm going to go control page, add a calculator page, hit menu, statistics. We're doing a statistical test, and a match pair T is treated as a regular T test, and we're basing it on data from the spreadsheet. Our null hypothesis is 0. Our list is hit the drop-down menu D, and make sure to change your alternative to greater than 0. And we record our information. We need the test statistic T, which is 1.2436. Our p-value of 0.1408. Notice it provides you with the degrees of freedom, but that you should know that simply for one sample T, it's just n-1 for the degrees of freedom. So we're going to record that information here. And since our p-value is greater than 0.05, we're going to fail to reject. Example 2. To compare 2 dog training programs, an Embedian school trained 43 dogs using Program A and 41 dogs using Program B. For Program A, the average number of training hours required was 24.8 with a standard deviation of 3.1 hours. For Program B, the mean was 22.9 hours with a standard deviation of 3.3 hours. Is there a significant difference between the 2 programs? Okay, so we have 2 separate samples, and the variable of interest is the average number of training hours, which is a quantitative measurement. So that's going to be a 2-sample T test. So we would define a parameter as mu A minus mu B. Now we're looking for the differences of the means as opposed to the mean difference. We have two separate means that we're comparing. So our null is we assume that there's no difference, that the two are equal. And the alternative, since they didn't provide us with a direction, we would do not equal 0. And so it would be a two-tailed test. When you have mu A minus mu B not equal to something, that means it's a two-tailed test. And again, I'm going to use 0.05. In this case, when we perform our data, we're going to enter the summary statistics. So again, I would start a new document. And you would do menu statistics stat test to sample t test. The method is summary statistics. And now let's enter our data. So we have 24.8 for training A with a standard deviation of 3.1, and we have 43 dogs. In the second training session, it was a mean of 22.9 with a standard deviation of 3.3, and training program B had 41 dogs. Make sure to scroll down. In this case, the default is mu1 not equal to mu2, but you just have to be careful of that. And we don't pool. And so in this case, when I scroll up, and you should always check to make sure you entered the data correctly, I get a t-statistic of 2.7168, a p-value of 0.0081, and when you're calculating degrees for freedom for the two-sample t, you need to run the calculator first, and you could either round up, round down. It's not going to make that much of a difference. So let's record that information into problem 2. And since our p-value is significantly less than the alpha, the significance level, I'm going to reject in this case. 3. 500 adults participated in the comparison of the effectiveness of 3 arthritic pain relievers. Each participant used one of the 3 medications for 1 month and then was asked if the product was effective. The results were as follows. Is there a difference in the effectiveness of these 3 pain relievers? So first of all, you have to decide what kind of test this is. So the variable of interest was based on the patient. Did they find it effective or not? Since it's a yes or no question, in this case, the effectiveness variable is a categorical variable. We also have 3 different treatment groups. So since it's 3 independent treatment groups, A, B, and C, it would be treated as multiple populations. So this would be a chi-square test of homogeneity. There's no parameter that you would use, but I didn't have room for the null and the alternative hypothesis, the statement in the area provided, so I put that in the parameter area. So with a chi-square test of independence, your null hypothesis is there's no difference, and in this case, the context is effectiveness of these pain relievers, and the alternative is that there is a difference. Again, I'm going to use 0.05, and when you're entering the data, we're going to be entering the data as a matrix. So we're going to go into our calculator, and again, we're going to set, especially with chi-square tests, it's a good idea to set up a new calculator page. So you would go enter the matrix. So you would go to the left of the book key, and you would want to set up a table. In this case, it is 2 rows and 3 columns, and make sure you write it exactly as it appears. And store it in O. So control var, that gives you the store function. Control var, and I'm going to store it in O. To run the test, you would do menu, statistics, stat test, and it's the same thing as a chi-squared two-way table. So option 8, and you would enter O. And you run the test. So let's record the information. So the test statistic is the chi-squared. Make sure you're using the appropriate notation. And that's 28.562. The p-value, let's just double check, hold on, is 6.28 times 10 to the negative 7th. That E is the same thing as times. So that's a really small value. And compared to the 0.05, since it's less than, you would reject again. Number 4, the manufacturer of a particular brand of microwave popcorn claims that only 2% of its kernels fail to pop. A competitor, believing that the actual percentage is larger, tests 2,000 kernels and finds that 44 fail to pop. Does the results provide sufficient evidence to support the competitor's belief? So the point of view is from the competitor. So the variable of interest is the number of popcorn kernels that, or the proportion of kernels that fail to pop. So, so either they pop or they don't pop. So that would be a categorical variable. And since it's only one sample, it would be a one proportion z-test. The parameter would be a p, or a rho, and that represents the true proportion of popcorn kernels that fail to pop. So we assume that it's 0.02, because that's what the manufacturer claimed, but the competitor thinks there are more that fail to claim. So that would be p is greater than 0.02. And I'm going to define alpha again to be 0.05. So we're going to get the test statistic, and what we're going to enter into the program is 44 out of 2,000. Okay, so let's go into the program. And again, I always think it's a good idea to start on a new document to avoid errors. And we're going to do menu, statistics, stat test, one proportion z-test, that's number 5. For p sub 0, you're going to enter the null, the 0.02. For the number of successes, you're going to enter 44. You have to enter an actual value, not a percentage. And for n, it's the 2,000 kernels. An alternative, make sure to change. And we get a test statistic of 0.6389 and a p-value of 0.2615. So this is Z is equal to, so for a proportion, the test statistic notation is a Z. Our p-value was 0.2615. And since that is greater than the 0.05, I failed to reject. Number 5. Dannon is supposed to put 29.6 grams of fruit in their fruit-flavored yogurt. To see if enough fruit is placed in the cups of fruit-flavored yogurt, a quality inspector measured the amount in 27 containers, so that's our N. She found an average of 28.9 grams, that's our X bar, and a standard deviation of 2.8 grams. Does this show that there's enough yogurt, or actually enough fruit in this yogurt? Okay, so the variable of interest is the amount of fruit in the yogurt. That's a quantifiable, it's measured in grams. It's a quantifiable measure. There's only one sample, so this would be a one sample t-test. And the degrees of freedom is n minus 1, so it would be 27 minus 1, or 26. The parameter is mu, the true mean amount of fruit in grams in yogurt, and I'm going to define my alpha as 0.05. For mu, the true mean, HO is going to be 29.6, because that's what the manufacturer is saying is supposed to be there. But she's suspecting that there's less. So she's a quality control, so she's seeing if there's less. Okay. We're going to now go to our calculator to enter our data. Again, I'm going to start a new document. So menu, statistics, stat test, and it's a t-test. And we're going to be basing it on summary stats. So mu is the 29.6 grams. Our mean was 28.9. Our standard deviation was 2.8. We had 27 containers of yogurt, and our alternative is that it's less than. She's checking if there's enough, and we hit OK, and we get a t-statistic of negative 1.299 and a p-value of 0.027. And since it's greater than 0.05, I failed to reject. Okay, and we'll do one more in this from this. A shoe manufacturer has developed a new running shoe that enables one to run faster. 8 adults participated in this experiment, in which each ran a mile with the regular track shoes and then ran a mile with new shoes. Their running times are recorded below. Is there evidence that the new shoe works better? Okay, so they have a faster running time. So first of all, since it's the same runner doing before and after, regular shoe versus new shoe, it's linked together. Also, we know time is a quantifiable measure, so this would be a match pair T. And and the degrees of freedom would be 8 minus 1, or 7. So mu diff is the true mean difference in running times. and you assume there's no difference, but you're assuming that it's faster. Now, I did old minus new. So that means that I would expect that the older shoe is going to have more time. It's going to have a greater time to run than the new shoe. So in this case, to show that the new shoe worked better, that you get a lower time. That would be a lower time if for performance for the new shoe, it would be greater than 0. So you have to be really careful about that. A lower time for running is better. So we're gonna, I already calculated the difference. And again, if you had gone the other way, if you went new minus old, you would have had a negative amount and you would have shifted mu diff to be less than 0. But this is how I calculated it out. And we're gonna actually enter the data. Again, I'm gonna start a new document. And I need a list in spreadsheet. And I'm going to hopefully quickly enter the data. And I would then go Control Doc, add a calculator page, menu, statistics, stat test, a t-test. We're basing it on data. This would be 0. The list would be D. And in this case, my alternative is greater than 0 because of how I set up my difference. And so I'm going to record that information. So the statistic is a t since we're dealing with means. Our p-value was 0.0271. And since it's less than 0.05, the p-value is less than 0.05, I'm rejecting HO.